thanks for inviting me. Thanks for giving me the opportunity to present this talk. It's pretty much a summary. I'm a computer scientist by training. I worked for a long time on personalization and recommendations. And then about a year ago, I jumped to the Australian Institute of Health Innovation, which is part of Macquarie University in Sydney. And I guess this presentation is a very condensed, very short summary of the kind of the key things that I learned over the year, and I'd like to share with you. As Helma suggested, it's pretty late here in Australia, 11 p.m. I probably won't stay around too long, but I'll stay for a little bit after the talk. So if you have any questions or anything, feel free to chat. Otherwise, I'll attend to the to the chat of the session probably Monday morning. I hope it will still be alive, and I'll address everything, all the questions. I'll just answer in writing. Otherwise, you've got the email. Feel free to contact me if you have any questions. All right, let's go ahead. So the presentation is broken down into 4 parts. First, a little bit about introduction and motivation, basically why I want to talk about these topics of well-being and then medicine and personalization for these areas. Then we'll talk about clinician-centric personalization, then about existing projects and an initiative around clinical decision support. And finally, we'll talk about the personalized side of this. One question that I forgot to ask Hannah or Helma, how long have I got?
Just a second. The next talk will start at 4:20. So you have an hour maybe for the talk and then some more time for questions.
Okay, no worries. I don't think it will take the whole hour, so we'll have more time for questions and discussion. Good. So maybe I'll start with just presenting how I got to work on these topics of health and medical applications. So I used to work for a reasonably long time. I had a 4 or 5 year project in the health space, in the well-being preventative health space. That's probably the best word to call it. Worked a lot on group recommendations and personalized technologies. More specifically, we worked on active games. Then a little bit outside the health space on recommendations of TV program and TV content. That was probably 2008 to 2012, 2013. We had this big project. All of it was surrounded around personalized technologies, user modeling, recommendations, and all those things. So the area is like very close to my heart. I've been working on this for a long time. And then after this, I jumped to the industry. Basically, I wasn't doing research at all. It was pure, I worked for Atlassian here in Sydney, and it was like pure data science, development of products, improvement of products, and so on. So it's kind of unrelated research, but it gave me like a very, very different, very interesting outlook and perspective on research and what research is important, what research needs to be done. And then I moved back to the academia, and this is my role with Macquarie Uni, where I'm currently leading a precision health stream at the Australian Institute of Health Innovation. And as the name suggests, we do a lot of AI applications of AI for medicine and healthcare. And this is precision health, and I'll be talking about precision health in a couple of slides. So first, maybe the project that the Tailored Lifestyle Information Project, the one that I just mentioned, that we had for 4 or 5 years, it was all about developing personalized technologies that would help people to maintain better health and better lifestyle. So there are probably, we had 7 or 8 different streams of activity, but all of them were around personalization, around supporting people, helping people to maintain healthier lifestyle, to monitor their well-being. So here is just a list, a very short list of topics that we worked on. There were there was a stream of work on personalized meal planning and food recommendations. Again, probably among the first papers that looked at and food and recipe recommendations. Then we worked on group recommendations or recommendations of food, still food for families. I led a large stream of work on activity motivating games. We also looked at exercise and essentially building exercise plans, personalized information access, social support in social networks, tailored social support in social networks. So it was all about, many interesting things, but all of them you can look at them as personalization, tailoring recommendations in the health space. So putting these kind of the presentation is quite pictorial, so there are not much text and mainly and a lot of pictures. So it was helping people maintain happy and healthy lifestyle. And then this is all those things that you have here, like being active, eating healthy, shopping healthy food, biking, running, jogging, staying active, energy balance, all those things. So if you look at the recipient of this personalized service, recipients of those recommendations, it was mainly about people, about what people in the clinical side, what they call customers, essentially. So not really customers, but it was not for clinicians. And basically, that was already kind of one of the things that we've been thinking at that time. Why do we not work with clinical people? Why are we always with the patients, with the real users? So when my current opportunity with AIHI came up, and it was in the precision health space, I said, yeah, it's very close to what I've been doing. I know a lot about this. It's even, some names call it personalized health rather than precision health. So just to put all of us on the same page, I've included a very, very short example, a very short description of precision health from UCLA Health website. So what you can see here in front of you, that's the short definition, a very intuitive definition that they give. So medical treatments are designed for the average patient. This works for some, but not for others, as each patient is unique. Where we live, our genetics, family history, and lifestyle all contribute to our well-being. Precision health, and that's the important bit, the last sentence, precision health takes into account difference in genes, environment, and lifestyle to formulate treatment and prevention strategies based on patient's background and condition. So these, of course, sounds very familiar for most of you because it's really close to personalization. It's really close to recommendation. The whole premise of say, recommendations and personalization is that people are different. And if you look, for example, at movie recommendations, different people have different tastes. So they'll be recommended different movies. So technically, like the idea looks very, very similar. We're all different. We have different genetic information. We live different lifestyle. So as such, treatment that's good for one person may not be good for another person. Or depending on, on our past medical history, one treatment, one drug may be good for one person, may not be good for another person. And in fact, this is also from UCLA Health. They even talk about, they put this picture, which says, okay, on the left-hand side, we've got genomics, which is, our genes suggest what disease we might be predisposed to, but it's an incomplete picture of human health. Yeah, sounds very familiar. There is like some background, some basic information. You can think of it as kind of demographic model. And I'm deliberately oversimplifying the things, or maybe long-term preference, sort of from the user modeling angle, more of long-term preferences. And then on the right-hand side, we've got the lifestyle or environment, which what they, again, at UCLA Health, they coined this as external factors like diet, exercise, medication, where we live, and all these influence. In this case, they talk about metabolic state, but you can think of it as, they do influence because there are all these built-in genomic or imprinted, probably a better word, imprinted genomic data And then on top of this, there are all those things that we experience as we live. And these two things from the right and from the left, they influence what they call phenotype, which is a snapshot of the current state of health. And then I forgot to mention this. And then the right-hand side, again, you can possibly consider this as kind of context. If we have this imprinted demographic model that's genomics on the left, and then the lifestyle environment on the right, then the two of them together build what we normally call a user model. And then having this user model, we can now personalize. We can going back to the definition at the top, we can take into account the differences and provide treatment and prevention strategies based on patient background and information. So we can, in other words, we can provide these personalized service. So I thought, yeah, like lots of things that are dealt with in the recommendation space, in the personalization community, they seem applicable because the problem looks like, very similar problem. Of course, very different application domain, very different goals, because product recommendation at the end of the day, it's about making money. Here we're talking about people, but yeah, it looks like a similar problem that potentially all those works, say in recommenders, can be applied and can help us develop these personalized treatment and prevention strategies. To my surprise, actually, when I got to Google and to read and to look for papers, I found pretty much nothing. So very few papers talked about the application of RecSys methods or like personalization, but kind of deep personalization, not simple rule-based personalization, but real AI-based personalization. Very few of these existed. So I said, okay, yeah, something has to be there. I looked at the previous editions of Health RecSys as the workshop, and then RecSys as a conference. I looked for health papers. I said, yeah, let's see what's out there. What have people been doing? And what you see in front of you is a word cloud of the titles, mainly the papers from Health RecSys, from the previous editions of Health RecSys, because there have been like 4 or 5 papers in the main conference. And then I just created this word cloud to see what are these papers about. I obviously removed the things like recommendations. I think also I removed the word system, because recommender system, it will be pretty much in every title. So this is what is left, right? So obviously you see this big health in the middle, which is obvious. Health RecSys would be talking about health. But other than that, the big things are, again, support, workout. On the left, you've got a whole bunch of well-being, daily shopping, eating, habit, food. Personalized is there, of course. So the only thing, again, it's pretty much what we were doing in the Tailored Lifestyle Information Project, supporting people, happy, healthy lifestyle, well-being, preventative health. You only see this medical at top right. But again, you don't see here things like, diabetes, drug, cancer, all those things which are kind of deep in the medical world. Mainly what you see here in front of you is again lifestyle, preventative treatment, well-being, and words from this space rather than from the medical space and from the healthcare space, which was, I should say, quite surprising. And I kind of wanted to dig deeper, and I wanted to understand why we don't see it. Why do we see mainly all those things? What you see in the picture, we're talking about patients as the recipients of the recommendations. We are talking about, again, food, exercising, jogging, all those happy, healthy lifestyle, shopping recommendations, meal recommendations, workout recommendations, again, for consumers, not for clinicians. And we don't see actually the other side, or we hardly see the other side, which is recommendations for medicine, recommendation for healthcare, diseases, drugs, medical treatments, medical procedures. We don't see recommendations for clinicians. We mainly see recommendations for consumers. And again, I wanted to understand this. Why not? Why do we have the well-being side overrepresented and the clinical side underrepresented? Pretty much not. Maybe 3-4 papers that that looked into this. So a few reasons that I came up with why lifestyle and well-being for consumers and not medicine and healthcare for clinicians. So first, there is a lot at stake. So if let's take movie recommendations as a counter example. If a movie recommendation goes wrong, the person will waste 2 hours of their time. Okay, it's not good. It's off-putting, but it's okay. We can live with this. Whereas if a drug recommendation goes wrong, or if a diagnosis recommendation goes wrong, it can potentially be a matter of life and death. So if the recommendation goes wrong, it's a really huge deal. The mistakes with recommendations, the errors are really, really bad, are really, really costly. So there is a lot of risk in recommendations in the medical space, and there is a lot of responsibility, of course, because there is still this kind of AI, or let's think about it as a recommender at this stage. So there is a lot at stake, and there is a lot of responsibility on that recommendation, even though we still have the human in the loop, because we will have the clinicians. They're not going anywhere, but the risk and responsibility are huge, which basically may make those recommendations too risky to be deployed. Another thing is the data. Like if you look back at RecSys as a space, as a research area, it moved a lot. It moved forward a lot due to the availability of data. Be those movie lens, the initial old movie lens data set that probably hundreds, if not thousands of papers used. Be the Netflix data set when they released it in the mid 2000s, which was a very strong boost. And then we saw all the latent methods and matrix factorization came from there. So the data was actually the kind of the means to advance the research area, whereas we don't see it in medicine. Why? Because the data is super sensitive. So it's very, the data is personal data, and sharing personal data, you are not allowed, because if you collect it, you have a whole bunch of ethics approvals, and in most cases they will not let you share the data because of the privacy risks. The patients will not agree to this. The ethics committees will not agree to this. In many countries, the legislation will not allow you to do it. Because imagine, personal information leaks and gets, say, to the hands of an insurance company. There is a huge risk here. So if there is no data, and the data is only accessible to the clinicians, it's not accessible to those computer scientists. They may want to do recommendations, and it's yet another hoop that you would need to jump through to do this work. So again, it's much harder. Not to mention the data is actually much more expensive, because if you do full genome sequencing, it's a matter of, say, $1,000, much more expensive than obtaining, let's say, a movie rating or a Facebook like. So there is no data. It's hard to advance the area and to do this research and develop those recommenders. And then the third thing, which is probably kind of the flip side of the lack of data, if there is no data and you cannot do statistical methods like matrix factorization, you have to resort to knowledge-based methods or content-based methods, which brings up the requirement for domain knowledge. It's really important to have domain knowledge if you want to do knowledge-based or content-based recommendations. And the area, actually, the domain of medicine and healthcare is much deeper than, say, the domain of movies, because there is much more knowledge, There are, of course, some ontologies and data representation languages, but still requires very deep domain expertise that, again, at the moment is just kind of is not there is not enough data, and there is this wealth of knowledge, so they don't go hand in hand. So bottom line, we don't see those things. We don't see recommendations for clinicians. We don't see recommendations of drugs and treatments and clinical procedures, which in fact is similar because, I mean, similar, it's not similar, but there are several other domains which I kind of can logically link to this. We don't see, for example, recommendations in nuclear power plants. There are no recommenders deployed there. Again, risk and responsibility. Like if a recommendation goes wrong, it's a huge deal. We don't see recommendations in courts. We don't see recommendations for large-scale investments like venture capitals, for example. Recommendations for venture capitalists that they just they did not exist. And if you want to invest a few $1 million, you probably will not rely on recommendations. And again, if you go back to the left, you will see all those things like, there is a lot at stake, so there are a lot of risk and responsibility behind those recommendations. There are no data sets of, court cases or, nuclear plant activity logs or something like these, or like investments. It's all confidential. And then if you want to do those recommendations, that would require highly specialized knowledge, like deep knowledge, and in several, in some domains, this knowledge is not represented in a form that the recommenders could deal with. And finally, the kind of the big question is actually, are recommendations needed? So, if you are, let's go with the last example with this venture capitalist. If you want to invest $1 million in a startup, do you really need a recommender that would help you and will tell you invest in company A and not in company B? If you are a doctor, if you are a clinician, and you've got a patient with a disease, and say there are 3 drugs to prescribe in this case, do you really need a recommender there that would say, no, drug C is the most appropriate drug in this case? So that's probably where we are going. Let's talk a little bit about this use case for clinician-centric personalization. I'm going away from the term recommendations and heading towards personalization. So what does it mean actually to deliver those clinician-centric personalization? What does it look like? What are the special things about it? What are the special characteristics? What are the things that you need to keep in mind when you deliver recommendations to clinicians rather than to consumers, rather than to end users? So clinician centricity, there'll be like 3 or 4 slides now talking about those learnings. What does it mean to develop? What does it mean to develop clinician-centric personalization? So first, those users, those clinicians, are highly knowledgeable users. So if you look at the doctors, it's probably a decade of training, and then these people, these people kind of they practice essentially. They see patients. They have a lot of knowledge. They have a lot of experience. And in most cases, this experience will come to this condition where they see a patient and they sort of very, very quickly form an idea what this may look like, what this disease may be, and what this treatment, what the best treatment will be for this patient, because they have seen already hundreds of people with similar symptoms and they've treated them, again, because there was a lot of training and a lot of practical experience that they gained. So they already have patterns of diagnostics and patterns of treatment, like what drug will work, what it looks like. Again, that's like that example that I had. If the doctor is not sure and say, okay, it may be disease A and it may be disease B, there are not too many options. And it's quite unlikely that all of a sudden it will be like disease disease X that the clinician has never thought of. It most probably going to be 2, 3, 4, 5 possible cases, and they have their own methods for diagnostics. Essentially, they rule out possibilities. Kind of, they have this huge search space that they start with a few symptoms, and then they start asking questions. They do pathology. They ask for pathology. They do blood tests, and kind of gradually they rule out options that kind of don't match the observed symptoms, and they're left with a few cases. And again, they have their previous knowledge. They have their previous history, which kind of, it looks like, there are only maybe a few other, maybe if it looks like a disease, maybe there are 2, 3 more options that may be there. Obviously there are still super rare cases that there'll be some very rare disease, but it doesn't happen that much. So again, I don't think there is really much space here for recommendations, because they are very knowledgeable. They know what kind of they see. They have their own patterns, and outside this space that they already have in mind, there is not much. There may be a few more options. So in short, not really information overload, not really a zillion of products to buy on eBay, or thousands of movies to watch on Netflix. That's not the case, right? They are time poor users. They, if you are a GP or a family doctor, you have a 15-minute slot to see this patient. You need to talk. You need to understand the complaint. You need to observe the symptoms. You need to explain these to the patient. You need to send them possibly to some pathology examinations. All this needs to fit into this 10 or 15-minute slot. So they can't really go and dig into papers. They need, they can't do too many things within this limited period of time. They need to make immediate decisions. So, again, not really that they have here space and bandwidth to explore too many options. They need to make immediate decisions. So again, we can't provide here a list of recommendations. Consider sending them to this test, or consider this drug, that just been released, and maybe this drug will work. Or, not even like go and see there is a paper that was published 2 months ago, and this paper refers to similar symptoms and similar conditions. It's really like time poor users. So almost like, top 1 recommendation that, if we were to deliver recommendations, that top 1 recommendation, top 1 suggestion that should work in this case. And again, it makes it hard. It makes this clinician centricity really hard. Moving on, risk-averse users. We talked about these. There is a lot at stake, and as such, they, things like serendipity and novelty are really not something that they're looking for. They essentially prefer really to stick to the territory that they know, not to go to this new space, not explore new options. In a sense, very, very conservative users. Risk-averse is probably conservative is a better word in this case. And something that's very related to this is kind of what I would call the Luddite users. They resist new technologies. Why do they resist new technologies? Because there is this thing, kind of, they're protective. Probably again, protective of their role is not the best word. They're kind of protective of their profession, because they have this concern that with the development of AI, human doctors will be developed by technologies that will potentially be examining patients and providing automated, let's call it automated diagnoses and automated suggestions. I don't think this is going to happen. Like, I really think in the near future, if we look at the next 10 or 20 years, we'll still have human doctors. We'll have human doctors that will be supported by technology. So it won't be doctors versus technology. It will be doctors supported by technology versus doctors as they are today, not supported by technology, or Luddite doctors not willing to be supported by technology. But essentially, they have this kind of intuitive pushback where they don't necessarily want these AI technologies, which again makes kind of makes the use case for this technology even more difficult, even harder. Which brings the next thing that I wanted to bring up. Trust is super important. So it's really important for the uptake of this clinician-centric personalization. It's really important to build and sustain their trust in the technology. So I think we're gradually moving from the focus on the users to the focus on this personalized service. How should this personalized service look like? And like with all the things that we just talked about, that they don't want, that they are risk averse, that they're conservative, that they push back and don't want new technology, that in the previous slide when we talked about they have a lot of knowledge, they don't have enough time. So essentially, if you want them to use the technology, trust is one of the key things here, which probably moves the focus a little bit from the algorithmic side and, how do I do the most accurate recommendations, most accurate personalization. It moves it towards the HCI side, which is actually how do I convince those users that don't really want this personalization, that don't really believe in this personalization. How do I still persuade them? How do I convince them to use this technology? And I think there is a lot of focus on trust. Again, and I'll elaborate on this a little bit in the next slides. Yeah, and here is one of the things actually that is probably the key component of building and of instilling and sustaining trust is explainability. And these words in no explanation, no value, these were actually exact words that I heard from clinicians. What if they were to use a decision support system, if they were to use kind of personalized AI to help them, the support has to be explained. Black box doesn't work. Black box is totally useless for them because, as I said, it's not really a technology that is about to replace this human clinician, but it's a technology that's about to support the human clinician. Well, the decision will always, in the near future, in the next, say, 10 to 20 years, the decisions will still be human decisions, decision by the doctor, but they'll be supported by the technology. They'll be supported by this personalized AI. And if they were to trust this AI, if they were to take on the suggestions delivered by this AI, they need to understand why. So if the system says, okay, drug A is the drug to prescribe in this case, they really need to understand what were the reasons that made the technologies to suggest drug A. So, and that's where we can delve into various modalities of this. So when we are talking, for example, text, there are things like summarization, that time for highlighting the most important bits, entity recognition, so essentially taking, for example, a 3-page discharge letter and converting and picking up the most important things and highlighting those entities, maybe even populating some medical form, some referral for a pathology. If it's an image, again, the technology needs to say, okay, I think that, the technology should say something like, okay, my interpretation of this image is X, and this is why I think, and some area of this image will be highlighted because this is what made the technology provide these suggestions. If it's an omic data, and I'll talk about this in a few slides again, like genomic data for the sake of this exercise, there was full genome sequencing that produced a vector of 20,000 dimensions. Here are 50 dimensions that were most informative, in a sense, feature selection of feature importance, right? This is why the technology thinks that this is the decision, that this is the this is the disease, this is the drug, whatever it is, whatever is dealt with. So this explainability in different modalities, in different sorts of documents, is absolutely critical in this case, I believe, because without it, if we talked in the previous slide about trust, and we said, yeah, trust, it's really important to instill the trust, it's really important to maintain the trust. Probably the most direct, the most immediate way to build this trust is explain this personalization. So explainability, like I genuinely believe explainability is super important. Along these come visualizations and interactive exploration, because again, for example, the genomic example that I used, 20,000 dimensions, they need to be able to be it visualization, be it access to the areas of to the areas of relevance, areas of importance. All those things are there, and this is another kind of sort of the flip side of this, that the applicability of non-interpretable AI is limited in this case, because, as I said, no matter how accurate this black box is, say deep learning, really like multi-layered deep neural net, and with very, very sophisticated architecture that produces really good accuracy in terms of the predictions, no matter how good this predictive accuracy is, if the functionality of this AI is a black box that cannot be interpreted, that cannot be inspected, and we cannot provide this explainability, like, okay, these are the reasons for providing this outcome and not that outcome. That's pretty much useless. Again, I'm sort of exaggerating and overgeneralizing a bit, but I think the explainability is really key, and the value of non-interpretable methods in this case is just limited, unless we can somehow use other methods to extract this interpretability and explainability. What else is there? We talked about this already. Errors are very, very expensive. Potentially, it's a matter of, as I said, matter of life and death. Accuracy is a priority because of trust and because of the things that we discussed. Obviously, even if you have explainability but the accuracy is poor, it won't build any trust. And issues of safety, again, because there is so much at stake here, and bad recommendations can literally kill people. Safety is an issue, and there is a whole area of safety in AI applications. Probably I won't mention this beyond this, like very brief. Another thing that's important is how we measure. How would you measure success of personalized AI? So we are used, like, let's start again with recommendations. We are very much used to these metrics of precision and recall, where classification accuracy metrics, we combine them into F1 or an F score in general. And in most cases, F1 will, like, it's a harmonic mean of precision and recall. And normally the weighting will be balanced. The weighting of precision and recall will be balanced, so both of them are equally important. We want high precision and high recall at the same time. Now, in clinical applications, they use two different metrics, which are not too far away. So they use sensitivity, which is essentially the accuracy of positive cases. So let's say we talk about cancer as a disease, and there is a group of people who have cancer. There is a group of healthy people. So sensitivity is essentially how many of those positives, how many of people who have cancer were diagnosed as people who have cancer. So that's the true positive rate, the accuracy of true positive cases. Error in this case means underdiagnosing. So underdiagnosing means somebody has cancer and they were not not identified as having cancer. So the system says that it's a healthy individual. They don't have cancer. So the person is underdiagnosed. Obviously, the implications are horrible, right? Because if somebody has cancer and this is not found, really, 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 really bad. Specificity is the flip side. Specificity is the ability of the system to detect the negative cases. So the ability of the system to detect healthy people, where the error will be the opposite. That's overdiagnosing. That's somebody who does not have cancer and they are diagnosed as if they had cancer. Error means overdiagnosing. One type of error is different from another type of error. So overdiagnosing, again, is underdiagnosing. Underdiagnosing, let's say they were predicted as they do have cancer, they're prescribed a round of chemo, which is, again, it's bad, but not as bad as underdiagnosing and not treating somebody who needs treatment with sensitivity errors. So, the errors are not the same errors. And I think the examples with cancer were pretty clear. And the type of errors is not the same type of error. Overdiagnosing is not like underdiagnosing. So the performance is not the same performance. The evaluation of the performance is not the same evaluation. That's another thing that I picked up. So back to the question that I asked when we just started this section. Is it recommendations or is it not? So I went back and I looked at the very, very old, like very first, very basic, I should say, descriptions of recommended systems. This is Resnick and Varian special issue, I think 1997. The very first thing that you see, it's often necessary to make choices without sufficient personal experience of the alternative. That's not what we have here, because those clinicians, again, I'm focusing on clinician-centric recommendations. They have a lot of expertise, they have a lot of personal experience, and they have a lot of knowledge about alternatives. Moreover, they will normally come with 2 or 3 alternatives that are plausible, that actually could already match the symptoms and the examination then observe. So even the first sentence kind of contradict the scenario that we have here. They are very, very knowledgeable. They have a lot of experience. They know a lot. So I would say no, it's probably not a recommendation. Another kind of example that I have here is the RecSys handbook, Francesca Ricci, Leo Rokach, and Bracha Shapira. So I highlighted here because there is a bit more text I highlighted. The highlighting is mine. Recommended systems are software tools and techniques that provide suggestions for items that are most likely of interest to a particular user. That seems okay. That's what we are. Like, we have, it's not really items of interest, but it is about suggestions for items that may kind of match the current case. But then let's go a few lines below. Recommended systems are primarily directed towards individuals who lack the sufficient personal experience or competence. That's not what we have. Again, that's very similar to Resnick and Varian. They have a lot of experience, and then the follow-up words, in order to evaluate the potentially overwhelming number of alternative items. Again, that's not what we have here, because, as I said, not only they have enough experience and enough knowledge, already in their head, they are primed to something. They're primed to a couple of options that seem reasonable in this case, and they don't have this overwhelming number of alternative items. They only have maybe another 2 or 3 that may fit the case. So again, kind of my thesis here is that we are not talking about recommendations. We are rather talking about decision support, which is different. Like, again, if I exaggerate it a little bit, it's almost like you don't want this say this playlist in YouTube where you finish watching a clip and then there is the next one that goes on immediately, kind of fully automated recommendations, sequence of recommended items that play. That's not really the case. Each recommendation each consumption scenario is different, if you wish. and it's really a decision that's made by the human. Do they prescribe drug A or drug B? Does it look like disease X or disease Y? And at the best, it will be a decision support that the technology will provide, and there'll be the human expert who will make the decision. So it's a second opinion. Essentially, it's almost like you have a doctor and you have a junior doctor providing their opinion, or less experienced, less trusted doctor that provides their opinion, of course, in form of technology rather than a real person. Interestingly, it is personalized decision support, because one patient, if you go back to the definition from UCLA Health, one patient is different from another, and what works for one may not work for another one. So one size does not fit all. There'll be different suggestions for different cases. So it is personalized, but again, we need to highlight this. It's personalized not to the clinician, it's rather tailored to the case, to the patient, to every person coming with. And what is this kind of personalization with the patient? It's to their symptoms, to their pathology, to the physical examination the clinician is doing, to the other diseases that they had before or they may be having currently, to their past medical history, to the medical history of their family, because they inherit things, and many, many other things. So it is an interesting use case of personalization, where clinician, the recipient of the personalization, is not actually the focus of the personalization, because we have the patient, we have this consumer in the focus, but then the recipient is clinician who already has a lot of knowledge, who is very time poor, who kind of pushes back against those recommendations. So that's what we're having in this case, this kind of personalized decision support provided to the clinician. All right. We are running a little bit out of time. So the next section, I actually wanted to talk with you about some of the projects that we are currently doing in this space. I guess I'll skip the example, but only present the high level framework where these projects fit, and probably mail me or talk to me offline if you're interested to learn about more about the specific project and specific things that we are doing, maybe more like 30 seconds for each one of them, and talk to me offline if you're interested. So first I want to talk a bit about the clinical process. So how does it work? What do they do? So the first and the main thing, the key thing that they're looking is the diagnostic. It's the diagnostic component, where basically they have this patient who is coming with a complaint, and they need to identify, to detect what disease or what condition is there. What is this? Is this cold fever? Is it COVID, or is it a normal flu? Once they have this decision, once they have this identification of the condition, there are two things that occur. One is the prognostics, essentially to predict which way this disease is heading. So they let's say they looked at the symptoms and they say, it looks like COVID. Is this person going to end up in ICU connected to the ventilator, or this person it's a young and healthy person and they just need to stay at home, and and in 2 weeks' time they'll be fine, right? So this is kind of the prognostic side, where they predict the progression of the disease, and then there is the therapeutic side, which is about determining the appropriate treatment. Let's say this person with COVID actually needs to stay in a hospital. Again, what drugs they need to be prescribed, or what procedures they need to be given. This is like this. Do they need to be connected to the ventilator, or just to be monitored in the ward and given some drug that help in their lungs, for example, right? And the interesting bit here that the last two, they're actually very, very intertwined, because part of the prognosis is actually this treatment, the therapeutic side. So with one, given one patient and given one diagnosis that they were given, and let's say the diagnosis is correct, with one drug, they may be fine in a week. With another drug, they may be fine in 2 weeks because the drug is, affects the body in a different way. And the same one, so that's where the treatment affects the prognosis. And it goes vice versa. It goes the other way around because this COVID patient, you leave him in the ward and they stay there, and then in 3 days' time, you see that their condition actually deteriorates, and you probably need a stronger drug to be prescribed because the previous drug didn't work. Or other way around, you see that the patient is improving, you can say, okay, fine, maybe we can now give another drug that will be less toxic, for example, will have less side effects. So the prognostics, and that's where kind of the prognosis affects the therapeutics, because you see the person is improving, they'll be fine in 3 days' time. Okay, maybe there is no need for a drug. So that's where the prognosis affects the treatment. So these two things go hand in hand, but they all start with diagnostics. So we kind of, why did I spend much time and presented these clinical processes? Because that's where many of our projects are. So we're mainly in the diagnostic space. And if I were to formalize the problem a little bit, I would probably say it's about providing decision support for diagnosis as a function of demographics, medical history, symptoms, examinations, pathology, and several other things. I think we don't have time to talk about all these examples, but there is a whole bunch of things that we are doing. Again, I shared the slides, and if you want, just talk to me, and we'll talk about this in detail. Then there is the prognostic space, where we have these prognosis as a function of diagnosis, treatment, and progression of the disease. That's the formal way. We do very little in this space. One of the projects that we are doing is actually about differentiating mild from severe COVID cases and trying to predict if a person will end up connected to a ventilator or they'll be fine. And the third one is a treatment where we are trying to predict the treatment as a function of the diagnosis, of the prognosis, and the progression of the disease. Again, there is, for example, one project we are doing here is trying to predict how melanoma patients will respond to a drug. Again, we unfortunately have no time to talk about it. So we talked about this. I'll probably go to the last bit, which is, okay, so we have a whole bunch of work that has been done in the personalization space, a lot of research, a lot of really solid, well-established, validated AI. Where does this fit? So I kind of picked 4 very, very high-level areas where personalization can fit. The first one is the user modeling side. So we have this breadth of clinical data that has been collected, be it examinations, blood tests, pathologies, past histories, electronic health records, hospital documentation, all those things. So how to model and present it as, how do you represent this user model, right? It's essentially a user model with a lot of information. How do you represent it? How do you use semantics? And there is a lot of semantics in this space, a lot of, as I mentioned before, ontologies. How do you use consumer level devices like all these wearables and mobile phones? They have lots of sensors. How do you use them to enrich these data? How do you integrate all these sources of data? You essentially have this kind of, some of them are images, some of them are textual documents, some of them are just numbers, for example. Some of them may be like genome sequencing data, very long vectors with lots of noisy data. How do you combine, how you aggregate, how you extract this multimodal information? How do you extract information from images, for example? How to cope with scarce data or potentially conflicting data, because when you aggregate data from so many sources, you may find some bits that are overrepresented and they're conflicting, some bits that are empty and nobody has ever done a particular type of blood test, for example. And finally, how do you select the right data? Again, we talked about genomic data as an example. When you do genome sequencing, A, it's very expensive and you can't do them to each and every person. B, you produce a vector of something like 20,000 bits, and you have these 20,000 bits, for example, for 200 patients, right? How do you pick the right information? How do you do machine learning? How do you do AI with this sort of data, with this sort of vectors of 20,000 features by 200 data points? That's a very difficult question. That's the user modeling side. The other side is actually the methods and the algorithms. We have all those, as I said, established, evaluated, solid, sound methods that were developed in AI or in RecSys specifically. How do you deploy them here? You would need to perfect this top one recommendation, top one decision support, because the clinician has no chance to examine more than this, or maybe top two, top three, right? So how do you improve the accuracy of this one? So your metric should be different, your algorithm should be different, because you really can't afford any mistakes in this top one recommendation. Do you need to develop it for each and every case, right? Because there are thousands of conditions and diseases, but surely some of those methods are transferable from one to another. And then even things like item-based and user-based inference, again, it's very similar to collaborative filtering, this sort of reasoning. But how do you actually, how can you do it? How can you deploy it for these applications of clinical data and specific clinical problems? How to make use of context? Again, we talked about these comorbidities as other conditions. For example, we have this, if you remember, there was this example of demographic model, and then there was lifestyle and environment, and all this created this phenotype. So that's the question: how do you make use of the right-hand side of this context, be it other conditions, other diseases of these patients, or be it the lifestyle, the environment side? How does this affect? Again, we know a lot about context-aware recommendations. How do you apply all those methods to this type of problems? And finally, we had all those what I called constraints around the explainability, around privacy, around data sharing. How do you around the limitations with sharing data? How do you meet all those constraints and still able to deliver this personalized decision support? And again, the focus here is interpretability and explainability, because yes, again, we have a whole bunch of those deep learning methods. Some of them, because they are black box methods and they cannot be interpreted, their accuracy in this case will be pretty much useless. Finally, the third one, it's not the final, there is one more. The third one is about user experience instruction, because I said we really need to keep and maintain trust. So now we have this question. Okay, we have this really sophisticated, really good AI that provides really accurate decision support, but then what do we do with this? Like, how do we build this trust? How do we show the decision support? How do we persuade the clinician to actually use to take up this decision support? The visualizations and interactive exploration, I already talked about these. They need to be able to see the reasons and potentially explore and see themselves. How to translate these technologies into practice, because the technology is deployed in the lab by a computer scientist, but it will be used by a clinician, say in a hospital. How can this technology be translated, and how it can be integrated into their existing processes? So again, from the HCI angle, it has to blend into the existing clinical processes rather than change those processes to make use of this technology by brute force. And the last thing, which I think is particularly important here and has to be mentioned, less of a personalization challenge, but more of maybe yet another constraint that has to be satisfied is around privacy and security. Very sensitive data that in many cases we're just not allowed to share it. Clinicians are not allowed to share it. If they share it, how do they share it in a private and secure way? So essentially, how do they share it so that nothing leaks, so that it's accessed only by those people who are allowed to access it? How do you, if we talk about interoperability and sharing across sources of data, how do you do it still in a safe and private way? And finally, more importantly, if you deploy AI to provide this decision support, how do you do it in a private way? So essentially, privacy enhanced AI. How do you, and again, some of those things were touched upon in the RecSys community, of course, in the broader machine learning community, about obfuscation and sharing of aggregated data rather than individual records, about privacy enhanced recommendations or privacy enhanced machine learning, and finally, even things like on-device predictions. So essentially, instead of me sharing the data and transferring it into the cloud to the model comes to me, and I do on-device prediction, on-device AI, or on my machine rather than in the cloud. So again, it's a practical constraint that will restrict what type of AI can be applied and what type cannot. And finally, that's the last slide. Really, over time, the last slide is about kind of my top three picks for areas that I think are really, really good and really, really exciting areas that can be looked into. The first one is knowledge discovery in high-dimensional genomic data. Again, back to this example of we've done genomic sequencing and we have a vector of 20,000 features. We have very few of them. Some of them, clinicians know that they are predictive of diseases, of conditions, of drugs, of treatments. But some of them, they've never studied. They've never looked into, just because this vector is so big and so long and there is so much information there. They know some bits are important. They know some bits are white noise. Some bits they just don't know. And I think that kind of discovery of knowledge in this high-dimensional omic data, and I deliberately use here omics rather than genomics, because there are lots of other things like proteomics, metabolomics, and other types of omics, what they call. They all share the same property, that they are they're very long, they're very hard to obtain, they contain a lot of information, and some of this information is big question marks. We don't know what it stands for, what it represents, and what to do with this, and what it can affect in this AI decision making. And that's where AI can help. The second one is specifically to neurological conditions. Lots of things occur in our brain, and we don't really understand what's going on. Like we know obviously that the brain is source of so many conditions and so many diseases, but we don't really understand we don't fully understand, I should say, the functionality and how it works and what affects what. With the development of really sensing technologies, there are a lot of EEG, MEG, and other sensors that are there. We can capture more and more information about the functionality of the brain. So with the development of deep learning and machine learning and more sophisticated data analytics tools, we can learn and we can understand better the functionality of the brain. So this can help both diagnostic of various conditions as well as prognostic, essentially saying, this person with Alzheimer's, this person is likely, for example, to develop Alzheimer's in 3 years' time. And the last thing that I already mentioned, again, pretty high level, is a lot of work is actually now on the application of AI for precision health, or personalized health. So we are working, we're taking those AI methods, existing AI methods, and we are applying them to medical and clinical problems. That's great. That's super important, because we first need to develop the technology. We first need to do it. But then immediately after this, there'll come the next question of how do we actually present this information to clinicians? How do we convince them that they need to use these technologies, that it's not going to push them out of their profession, but it's going to help them make better decisions and more accurate decisions. So I think this move from AI for personalized health to personalized interaction with this AI, it will probably start, my hunch, pretty soon. And I think, again, this is kind of that's where RecSys as an area sitting at the intersection of machine learning, AI, and HCI on the other side. That's where the methods developed in the RecSys space can have profound impact. So this was the last slide of the presentation. I'll leave this one on, and I'm happy to take questions. Okay, I'll stop sharing, and I'm happy to take questions.
And my name is Lars Böcking. Thanks for having me. And in this work, we want to look at the application of reinforcement learning to suggest clinical pathways for an individual patient. And a clinical pathway describes the treatment and rehabilitation procedure for an individual patient, which maps to the exercising recommendation mentioned by Mr. Berkowski in his talk. He also raised some concerns about the risk and responsibility later in his talk, which we would like to shine light on in the field of reinforcement learning and imitation learning. So depending on the current state of a patient, a decision is to be made on the next measures to be taken. So the patient condition can be the describing of his or her disease pattern, his clinical values such as heart rate, blood pressure, but also medical surveys like the Borg scale, evaluating the level of exhaustion. And such sequential decision-making processes could well be outsourced to a reinforcement learning agent, as they are based on exactly this concept described as a Markov decision process. However, reinforcement learning is generally funded on a try-and-error approach. So the agent selects an action AT at a timestamp T and observes whether or not its action had a positive or negative impact on the patient, represented by the change in state of the patient and quantification seen in the reward. So we would like to address two central questions. How can we emphasize the importance of safety in suggesting rehabilitation treatments to a reinforcement learning agent? So this question is crucial to develop an RL agent that does not violate safety constraints and never puts the patient at risk by suggesting dangerous rehabilitation measures for an individual patient. And secondly, how can an agent explore the individual optimum and still remain within a safe and medically acceptable action space? So, however, to find the optimal clinical path for an individual patient, the system needs to explore different configurations and parameterizations of those rehabilitation activities. Therefore, the agent needs to be able to look for individual optimal once the patient is in a sort of uncritical state. And to do so, as also mentioned in the previous talk, we quite often have access to domain experts, where we can watch demonstrations and learn from them how to deal with critical conditions. This approach is generally referred to as imitation learning. So one trains the policy of an agent in such a way that in a given state S, it chooses the same action A that was observed by the expert in a similar state. So we want to train a policy, pi, that minimizes the difference in the suggested action to the action observed by the expert demonstration. And our approach to avoid critical states is to take the actions demonstrated by the experts whenever the value in one dimension of the clinical states is particularly high or particularly low. So those are the critical states where we do not want the reinforcement learning agent to explore for the most optimum suggestion, but to rather stick with the demonstrations that was observed by the expert. So if the agent is confronted with a patient whose heart rate is at the edge of the distribution of observation features, the agent should know how an expert has reacted in a similar critical state and suggest that same action in order to handle the critical condition. To do so, we identify, this was too fast. Okay. To do so, we identify demonstrations where one or more observation features is at the edge of the distribution, and those critical demonstrations are then used to train a safety-aware policy by imitation learning, which we have described previously. So to summarize, if we train the agent policy on these examples on handling critical situations, the agent learns to react specifically to critical developments while being free to explore uncritical states to find the optimum parameterization of activities for an individual patient. And I think this was around about 4 to 5 minutes. Thank you for your time, and I'll be happy to answer your questions or get into discussion on further development and application of this concept, this approach. Thank you.
We are very happy to welcome you to the first long paper presentation that we are doing today. And it will be presented by Purnima and Patrick, and you have the stage.
Thank you. Hello, everyone. Today, I would like to present our work on the importance of context, privacy perceptions of general versus health-specific data in health recommender systems. Before directly diving into the presentation, I would like to give an overview of what we are going to present today. And I would like to first start with the question what motivated us to do the study, and then I would also talk about some related work, and then Patrick would take over and he'll talk about the method and results section, and then again I would come in and talk about the conclusion part. So we have all been in a situation where we have fallen sick and know that the right thing to do is visit a doctor. But the first thing we do is go online and look up the symptoms. And before we know, we are in this rabbit hole where we self-diagnose ourselves and conclude that the situation is a lot worse than what we thought. That happened because we scout the specific websites that take almost no information from us and give a generic overview of the diagnosis associated to the symptoms. Whereas there are also applications on the sites that are specifically designed to assist users to get correct or more accurate information about their health. But they ask us to fill us this long surveys wherein we have to give our health information or personal information, and we are not very comfortable doing that. This motivated us to ask the question, how much information are we willing to share? So we first started looking up answers for that question and realized that there are many fellow researchers who have asked similar questions. Lee and his colleagues, in their research in acceptance of wearables in health sector, found that people conducted risk-benefit analysis, where they compared perceived risk versus perceived benefits of using a device. If the benefit outweighs the risk, then they would gladly use the device. The process where they conduct the risk-benefit analysis to decide which personal information to provide is also called as privacy calculus. They also found that people who were frequent computer users or the ones with higher level of educations were more willing to share their personal information. In another study conducted by Kane and Hanania about what type of information users are willing to disclose, they found that users are less willing to disclose sensitive data like something related to sexual health or mental health. Frost and his team, when conducted an analysis of cancer communities online, found that patients with poorer health were more willing to disclose their data. There are also other studies which have shown that previous experience on the internet, specifically a bad one, gender, age, and technology self-efficacy are some factors that inhibit the willingness to disclose the data. However, decisions to use health recommender systems has been a balance between benefit and concern, and context plays a very important role. Keeping that in mind, we built the aim of the research to identify general and health data the participants consider to be sensitive, or to study the differences in willingness of the participants to disclose more sensitive data, and to study the influence of different user factors on the willingness to disclose the data. Patrick would take over from here.
Did you mute? Let's see. So to fulfill this aim of research, we conducted an online survey, and this survey consisted of 3 parts. In the first part, we there it is. In the first part, we collected some demographic data. We asked our participants about their perceived health and also about their smoking habits. In the second part, we collected further information about our participants and about their technology self-efficacy, their health and privacy concerns, and their institution-based trust and distrust, and also their disposition to trust. And in the last part of our online survey, participants had to disclose, state their willingness to disclose health and personal data in 3 different contexts. And we chose 3 different contexts to show some examples for the application of recommender systems. And the first context was to achieve a healthier lifestyle. Then the second context was to self-diagnose health complaints. And the third context was to inform yourself about drug prescriptions using a recommender system. And for doing so, the participants had to choose how much data they are willing to disclose. And for data, we divided into general data, like the date of birth, gender, the height, and the weight of the participant, and also the health data, like pre-existing conditions, chronic illnesses in the family, allergies, current medication, information about diet, alcohol consumption, and smoking behavior. And we also informed the participants that if they would disclose more data, then they would also achieve more precise results. And for our study, and also based on the previously introduced literature, we formulated some hypotheses. So, for example, we assumed that for the drugs information context and the disposition and a higher disposition to trust, there is a higher willingness to disclose data. And on the other side, for the health data compared to the other data, and also for participants with negative internet experiences and lower institution-based trust, higher age, lower technology self-efficacy, and also concerning the gender, that the willingness to disclose the data is lower. So to describe our sample, we conducted a snowball sampling using Facebook, and had in total 163 participants in our sample, of whom were 108 women and 53 were men. And the average age was 28.8 years, and most of our participants were non-smokers. They had a rather low technology self-efficacy and a rather high institution-based distrust concerning the handling of personal data. And on the other side, also a low institution-based trust concerning technical infrastructure. They had high privacy concerns and a high disposition to trust. To further on describe our sample, we now look on some correlations of our independent variables. So at first, we can see that with higher age, the institution-based distrust in the handling of personal data gets higher, and the disposition to trust decreases. And for participants who reported more computer self-efficacy, we can see that the privacy concerns are higher, and the institution-based distrust on handling of personal data is also higher. And for the privacy concerns, we can see that with higher privacy concerns, our participants had higher institution-based distrust in the handling of personal data, but simultaneously, at the same time, also a higher institution-based trust in the technical infrastructure. And for the institution-based trust in the technical infrastructure, we can see that with a lower trust, there follows also comes a lower disposition to trust. Looking now into our results, we can see, we can have a look on our 3 different contexts and the willingness to disclose the data. And we can see that people are most willing to disclose general data for healthy life, and less willing for looking up health complaints, and least for the drugs context. And also we can see that the more sensitive the use case is, the more participants were willing to disclose health data. So for the drug information context, the will was the highest, followed by the health complaints, and then the healthy life. And if we now have a look into into all the data types, we can see that overall the willingness to disclose data is for general data always higher than for health data. And for general data, we can see in special that the day of birth is the least wanted to be shared. And for health, the willingness to disclose data differs between contexts. So for example, for the hereditary diseases and also the medicine intake, the picture is very clear, whereas concerning eating habits and sleeping data, participants did not differentiate clearly between the contexts. So as a result, so in the effects of user factors we could see in our study were that with higher health concerns, there's also a higher willingness to disclose general data for all the 3 contexts in, and also for health data in the healthy life context. And with a higher disposition to trust, our participants were more willing to disclose health data, also only in the healthy life context now. And lastly, there were no influences of age, computer self-efficacy, privacy concerns, or institution-based trust. And yeah, this leads us to the conclusion, and Purnima will take it from here again. Let me just quickly show.
So to conclude, we conducted this study to see the user's willingness to disclose data in 3 different application contexts, and the effects of the user diversity factors in the willingness to disclose data. Reviewing our hypothesis again, we found that the users were more willing to disclose other data compared to the health data. So our first hypothesis holds.
To move a little bit to the right.
Yeah.
Wait. There it is.
Yeah. Okay. Different contexts had a significant influence in disclosing the data. We believe that users are more willing to disclose their data for context drugs to find drug information, as this is where as in this context they could see the strongest benefit preventing potentially dangerous side effects. Here, the more sensitive the context is, users were more willing to disclose their data. However, we also saw that users were less willing to disclose the data when it came to finding about the health complaints context. So our fifth hypothesis, which is users who had higher disposition to trust were more willing to disclose the data, also holds. And the remaining hypothesis, where we tested the user factors and their influence on willingness of the users to disclose the data, did not show any strong effect in our study. So that brings us to the end of our presentation. Thank you. and we would like to take any questions from here.
Hello everyone and welcome to this presentation. My name is Vaibhav Pandey and I'm a graduate student at University of California, Irvine. Today I'll be presenting a work about personalized user modeling for context-aware lifestyle recommendations to improve sleep. So first let's talk about why sleep is such an important problem to address in our day-to-day lives and for managing our long-term health. So sleep is the natural repair mechanism for our body. It is essential for converting short-term memories to long-term, and studies have also shown that a good night's sleep improves learning. And whether you are learning maths, how to play the piano, or how to perfect your golf swing, sleep helps enhance your learning and problem-solving skills. Sleep also helps you pay attention, make decisions, and be creative. Sleep deficiency may lead to trouble making decisions, solving problems, controlling your emotions and behavior, and coping with change. And sleep deficiency has also been linked to depression, suicide, and risk-taking behavior. Sleep also plays an important role in our physical health. Sorry. Ongoing sleep deficiency is linked to an increased risk of heart disease, kidney disease, high blood pressure, diabetes, and stroke. Even our immune system relies on sleep to stay healthy. For example, if you're sleep deficient, you may have trouble fighting common infections. And lack of sleep can also make you less alert and affect your coordination, judgment, and reaction time while driving. Studies have shown that going too long without sleep can impair your ability to drive the same way as drinking too much alcohol. So for such an important part of our lives, let's look at all the methods that we utilize to monitor and measure our sleep. So the current gold standard for clinical data collection related to sleep is a method called polysomnography. It requires the person to sleep in a controlled environment with multiple sensors attached to their bodies. And these sensors measure the person's physiological responses such as ECG, EEG, EMG, and respiration flow while they're sleeping. And while the data provided by polysomnography is very accurate and multimodal, it's difficult to replicate this study in a person's natural sleeping environment because of all the sensors required. And the sensors also change the person's sleeping environment so that it's not natural anymore. And another clinical method for collecting sleep data is called actigraphy, and a lot of consumer applications and devices rely on that method. So there are wearable devices such as an Aura Ring or different smartwatches which collect sleep metrics based on accelerometer data that's present on the device. And many of these devices also capture the user's heart rate data while they're sleeping. And there are applications like Sleep Cycle which utilize ambient noise data to capture a person's movements or their behavior while they're sleeping. So while these applications can provide useful insight in a person's sleeping habits, they do not explain how other lifestyle behavior impact the person's sleep. For example, what we do during the day definitely has an impact on how we sleep. Lifestyle habits such as diet, work and exercise patterns, and different environmental factors like temperature and humidity govern our sleeping habits to a large extent. While various scientific studies have explored these relationships in a controlled experimental setting, those insights are valid at a population level and may not generalize very well for every individual. However, we can utilize the data generated by the individual to create a personalized model that captures these relationships for every individual. We live in an era of unprecedented data generations, and every day an individual generates a large amount of multimodal data streams, and different applications capture data about different aspects of our lives, such as sleeping, eating, and exercises. And however, most of the data collected by these applications resides in individual silos and first needs to be brought together to leverage it effectively. And once we have the aggregated life logs, we can utilize cybernetic principles for recommending actions to the user that will take them closer to their predefined goals. In this work, we have attempted to do this for optimizing sleep quality, but the same principles can be applied to other health goals as well, such as managing diabetes or other chronic conditions. At the heart of this cybernetic loop lies the personal model, which encodes how different events in a user's life are related to each other and how do they impact the user's health state. We have used interval algebra and event mining to create a rule-based explainable model of the user's sleep that can be used to understand and predict sleep outcomes. So we used an event pattern language derived from Allen's interval algebra to represent temporal relationships between events. Every event pattern has at least two events that are related to each other through a temporal constraint. For example, pollution exposure is usually followed by difficulty breathing. High humidity events are frequently concurrent with sleep interruptions. And if a person intakes some alcohol 3 to 4 hours before they go to bed, they usually exhibit sleep interruptions. And we can also use event operations to create new event streams from the existing ones. For example, we can create a new event stream called exercise that includes all the events from running, walking, cycling, and swimming event streams. And then we can use this newly created event stream for our analysis. Now, every event during a user's day has some impact on their health. And this can be quantified by certain attributes of the events. For example, for exercise, the attribute might be calories burned or exercise duration. Or in some cases, there might be sub-events during the lifestyle event which are relevant for our health state, such as REM sleep or slow wave sleep event during a sleep event. We call such events health interface events, as these are the events that are relevant to a user's health state. We utilize the event pattern language to specify patterns relating to or more events and search for those patterns in the user's event streams. A set of rules and behavioral patterns represent possible causal relationships that determine the person's behavior and biological outcomes and need to be tested while controlling the effect of confounding factors. We do this by using something called a hypothesis verification operator, which creates different subsets of the input and outcome event pairs based on the values of the confounding factors and find the effect of the input event on the outcome. The verified rules are added to a rule-based personal model of the user, which can be used to make predictions and provide recommendations in different contextual situations. So in this example, you can see that we are trying to test the relationship between temperature and my sleep quality. And we are trying to control the variable that is exercise levels during the day. And the exercise event has 3 different levels, that is high exercise, medium exercise, and low exercise. So we end up with 3 separate event subsets, which 3 separate subsets which contain pairs of temperature, exposure, and sleep quality at that night. And within each subset, we find the statistical significance of that relationship and the likelihood of different sleep outcomes. And the rules that are found to be significant are added to a personal model. And this model can be updated over time as we observe more occurrences of this relationship between temperature and sleep. Now, as new events appear in the user's daily event log, we derive the relevant interface events from the different lifestyle events and add the health parameters to the user's context. These contextual variables need to be defined in advance and will depend on the types of events that are available in the user's life log. Thus, any new event that happens during the user's daily life can change their current health context, and we need to generate a new set of recommendations every time the user's context is updated. These contextual variables would need to be matched with confounding factors and the input event for different rules in the personal model. We choose the rule that matches the current contextual variables while maximizing the likelihood for the desired sleep outcome. For example, in this figure, after the dinner event, the user's context has information about their exercise levels, stress levels, last night's sleep quality, and and time of meals for the day. The last variable, that is the time of meal, was obtained once the dinner event was over. We match the available set of variables with all the rules and find that the closest match is rule B, as rule A does not match with the user's exercise levels during the day. The confounding factors and the intervention event that do not yet have a value, that is temperature, or whose values can be changed with new events such as stress, are considered as items that can be controlled and are generated as recommendations. These recommendations can be sent to an automated system, such as an HVAC system that controls the aspects of user's environment, or can be sent to the users themselves if it's an action for the user to take. For example, meditating to reduce stress would be an activity that would be presented as recommendation to the user. Now, we tested the system with the data generated by a 31 years old male athlete. This person used a Garmin Phoenix 5 smartwatch, two smartphone applications, Sleep Cycle and Strava, and an IoT device called Sensor Push to collect data about their daily life, about their sleep behavior, and about their immediate environment, such as local room temperature and humidity. And we applied thresholds on these data streams to convert these data streams to events so that we can apply our event mining approach on these event streams. So this table displays different thresholds that we applied on different sleep parameters. And similarly, we applied different thresholds on different exercise and lifestyle events and parameters as well. And once we derived the event-based data, we performed two types of experiments. So our goal was to create an interpretable user's model of the user's sleep, which can tell us about the average effect of different lifestyle events on the user's sleep outcomes. And in the second set of experiments, we created models to predict the person's sleep outcomes in specific contextual situations. And we compared two types of modeling strategies, one a static model and the other was an online model which adapted with the user's changing sleeping habits. So the first step was finding out what are the significant confounder variables for different relationships between lifestyle factors and corresponding sleep outcomes. And this table displays all the confounding variables that we tested for different pairwise relationships. And some examples are that for the relationship between sleep latency and the exercise minutes during the day, the time of meals proved to be a very significant confounding variable. And similarly, for the relationship between the time of meals and sleep quality, exercise minutes was the only significant confounding variable. Now, once we have the set of confounding variables that can significantly impact a relationship, we needed to find out what's the impact of the input event or the intervention in different confounding situations. And to do that, we compare the distribution of the sleep outcome parameter, which has co-occurred with different levels of the input event. So for example, on this slide, we are trying to find out what is the impact of time awake between two different sleep events and how much that impacts the awake minutes or sleep interruptions during one sleep event. So we have three levels for this event, and we designate one of these event levels. For example, minutes awake between sleep events as greater than 17 hours as the baseline event, and we compare the corresponding distribution of sleep outcome for the other event levels with this baseline distribution. And from this slide, we can see that for poor awake minutes during the last night's sleep, we find that staying up for more than 17 hours leads to a good quality of sleep with regard to awake minutes during the sleep event. And once we have identified the effect of different lifestyle events in these different contextual situations, we find the average of those effects, and we have displayed that in this chart. And as we can see, for this particular individual, increasing exercise duration leads to improvement in all sleep outcomes, while both high and low temperatures lead to worse sleep latency as compared to average temperature. Now, we also trained two sets of linear regression models for predicting sleep outcomes in different contextual situations. And we wanted to compare the difference between an adaptive model versus a static model. We plotted the RMSE errors for the two sets of models, and as expected, we found that the two models start at about the same error levels, but the adaptive models is able to improve its performance over time as it changes with the user's changing sleep habits. Now, for future direction, we want to improve the quality of a model by incorporating further lifestyle events and data streams. For example, events related to a person's stress levels and their nutritional intake. And we also want to integrate knowledge-derived rules and provide an easier interface for domain experts to use to initialize a person's sleep model using known scientific results. And our current recommendation system operates in a greedy manner, and it can optimize one sleep outcome, but if a user wants to optimize multiple outcomes at the same time, which is very likely in a real world scenario, then this greedy approach will not work, and we'll have to find a more efficient way to fulfill that. And we also want to experiment with more sophisticated models for predicting sleep outcomes, as currently we are utilizing simple linear regression models. Thank you for listening to this talk. And if you have any further questions about the event mining methodology or our experiments, you can email me at this email address, and we can move on to the Q&A session now.
Okay, so hi everyone. My name is Florian. I'm a postdoctoral researcher from the University of Glasgow. And today I am going to present a recommender system for healthy and personalized recipe recommendations. So the main motivation behind this work is that unhealthy eating is becoming a pretty serious issue worldwide. As you can see on this map from the World Health Organization, more and more people are getting overweight, and obesity is spreading, which can lead to pretty serious health issues such as cardiovascular disease or diabetes. So if we want to avoid these risks, we definitely need to find a way to change people's eating behavior and to make them eat healthier food. There are many existing ways to tackle this problem. One solution that targets a wide audience is to develop advertisement campaigns trying to promote healthy eating, trying to explain what is a healthy diet and what are the benefits of eating more fruits and vegetables. Another solution is to directly print nutrition information on products. Traffic light systems from the Food Standard Agency can, for instance, help people to quickly identify whether a specific food is low in fat, sugars, or salt. But some other solutions can be applied locally. For instance, restaurants can nudge people towards healthy eating simply by reducing the size of their plates. Customers will eat less, but they are still satisfied because the plate looks full. Another nudge technique is to make healthy food more convenient to pick, simply by putting the food on specific shelf in a shop, or by adding a line in a high school canteen specifically dedicated to healthy food consumption. And finally, one solution that I'm particularly interested in is to change the way people look at recipes online by developing recommender systems that reconcile people's preferences with healthiness. That's the kind of solution I'm going to talk about today. Over the years, many food recommender systems have been developed. And one of the main challenges for the systems is to deliver the most accurate recommendation that will match users' preferences. When we look at the literature, we can mostly find two different approaches that are competing: content-based approach versus collaborative filtering approach. Each approach has its pros and cons, but the recent paper from Hartner et al. Showed that collaborative filtering was actually performing better than content-based algorithms in the food domain. But the thing is, most of these systems rely on datasets that were scrapped from online recipe portals for their recommendations. And one issue with these portals is that most of their recipes are unhealthy. They will often recommend unhealthy food, which leads to a second challenge, which is how to recommend recipes that are not only matching people's preferences, but are also healthier than what they usually eat. So here again, there are some work that try to solve this problem, and they do that by mostly biasing the outcome of the collaborative filtering algorithm with a health score that is computed based on the recipe's nutritional value. However, most of these systems are evaluated objectively, and they do not really try to see whether real users will actually pick the recipes they would recommend. And that leads us to our two research questions. For the first one, we want to understand whether people are willing to pick recommendations that are healthier than what they usually eat. And for our second research question, we want to investigate the influence that a simple health tag can have on people's decision making. So our first step to answer our two research question is, of course, to build a recommender system. So to recommend recipes matching users' preferences, we followed Stratner et al. Paper and we relied on collaborative filtering. We scraped our datasets from the website allrecipes.com, and to get a dense recipe user matrix, we only scrapped recipes that were rated at least 25 times and users who rated at least 30 recipes. We tested 4 different collaborative filtering algorithms to train our system, and finally took the alternate least squares solution, which obtained the best average area under the curve over 100 trials. To determine the healthiness of the recipes of a dataset, we relied on the Food Standard Agency guidelines to compute a health score. In these guidelines, each of the 4 nutritional values that are fat, saturates, sugars, and salt is associated with a score and a level depending on the amount of nutrient present in the recipe. For example, a recipe containing less than 3 grams of fat for 100 grams can be categorized as low, and that will add 1 point to the final health score. On the other hand, a recipe containing more than 17.5 grams of fat for 100 grams is categorized as high and will add 3 points to the final health score. So in the end, we have an overall health score for a recipe that varies from 4 to 12, 4 being the healthiest and 12 being the least healthy. So finally, to recommend a recipe that matches users' preferences and that is also healthy, we designed the following recommendation process. The system first collects a user's profile in the form of a list of recipes that he or she likes. Based on this user profile, the collaborative filtering approach will predict how much this user will like each of the recipes in our dataset. This collaborative filtering score varies from -1 to 1. For each recipe, the system also computes the health score based on the FSA guidelines. The system then combines these 2 scores using the formula below here and rank the recipes according to these scores. The recipes at the top of the list are the recipes that best correspond to user profiles and are healthy. Then the system picks the 5 best recipes and recommend them to the user. So now that we have a system that can recommend recipes that are both healthy and match user preferences, we can design an experiment to answer to our 2 research questions. In our experiment, we choose 2 independent variables. The first one corresponds to the recommendation mode. We built 3 different systems. The first one only recommends the healthiest recipes in the database. It only relies on the FSA score. The second one recommends recipes that match participants' preferences. It only relies on the collaborative filtering predictions, while the last one recommends recipes that are both healthy and match participants' preferences. In addition to the recommendation mode, we have also a second independent variable that corresponds to the tag mode. And for each of these 3 systems, we have 2 different versions. One version where a health tag is displayed on the recipe, and one without a health tag. So in total, in the end, we have 6 different conditions. During the experiment, each participant follows the same procedure that consists in 3 steps. We first ask users to pick at least 5 recipes they like amongst a grid of 30 recipes selected randomly. Now that we have a profile, the system can recommend 5 top recipes depending on the condition. These recipes are then presented to the participants in a grid along with 25 other recipes selected randomly. Here, we ask participants to select the 5 recipes they like the most. Once that's done, we ask them a few questions and collected 118 interactions on Amazon Mechanical Turk. Besides the F1 score of the system and the health score of the recipe selected, we measure in our questionnaire user satisfaction and perceived ease of use. So these 4 different variables here are our dependent variables. Our results show that, as expected, the system recommending healthy recipes performs significantly worse than the 2 others. What is interesting here is that although the F1 score of the preference-based recommender system and of the hybrid system are similar in the condition with no tag, the performance of the hybrid system decreases when the recipes recommended are displayed with a tag. The parallel here can be made with the results we obtain for the ease of use. It basically looks like it was harder for participants to pick recipes when the 5 recommended recipes were both matching participants' preferences and were healthy. One potential explanation for that is that all the recipes in the hybrid condition had very similar health scores. All of them were in orange or were moderately healthy. Whereas the 2 other conditions introduced recipes tagged in green, like for the healthy recommendation mode, or in red for the preference recommendation mode. Overall, we noticed that people were more satisfied with their choices when they were informed about the recipe's healthiness. What is more interesting here is to look at the average health score of the 5 recipes selected by the participants. When tags were present, recipes selected in the pref-based condition were slightly healthier, but the impact was the opposite when participants were delivered healthy recipes only. So basically, people will avoid recipes tagged as unhealthy, as well as recipes tagged as unhealthy. The first part can partially be explained by the fact that people usually associate a feeling of guilt with unhealthy food consumption. So people are less inclined to pick unhealthy recipes if they are explicitly informed about their unhealthiness. The second part can be explained by the healthy equal less tasty effect, which describes how people tend to associate healthy food with low tastiness. We basically assume that participants in our experiment were less inclined to pick recipes explicitly tagged as healthy because they thought such recipes would be tasteless. So to conclude, we presented today a system that was able to bias the outcome of collaborative filtering algorithm to recommend recipes that were healthier than what people would usually eat. We found out that the performance of our hybrid system was almost similar to the performance of our system that only recommended recipes matching users' preferences. In the end, we noticed that the tags were actually pretty helpful, but we also noticed that informing people about the healthiness of the recipe might trigger the healthy equal less tasty effect. So having tags is actually a double-edged sword. In the future, we would like to change the way users interact with our system by taking a conversational approach. That will help us to collect more fine-grained preferences during the interaction and will also allow us to go from the collaborative filtering only to a hybrid approach, either by introducing a knowledge-based approach or content-based approach. Finally, we would also like to investigate whether adding explanations would change our system performance, and more importantly, if it would influence people to pick healthy recipes more often. Thank you for your attention.
So yeah, hello everyone. My name is Yoga Thiessen. I'm a research assistant professor at the Department of Bioengineering at the University of Illinois. And today I'm going to talk to you about our position paper titled A Dynamic Human in the Loop Recommender System for Evidence-Based Staging of COVID-19. This is a collaborative work with others at University of Illinois in Urbana-Champaign and also at Chicago. So based on what I have seen so far, I think this talk is going to be a little different. I hopefully this will be interesting to you. So as you all know, COVID-19 is an extraordinarily complex disease, and we have about 32 million infections and 1 million deaths so far. And the primary reason for that is there is a varied range of clinical practices in how the disease is assessed and treated. And that leads to variability in the death rates among across the world. For example, countries like the US and Brazil have higher death rates compared to other countries. So what is the reason? And in addition, the recovery percentages, how many people who are infected actually recover. They also are related to the clinical practices, as well as I think from the previous talk, there is also varied ranges of health concerns among different countries related to obesity and all of that. So what we think could be a solution to all of this is developing a staging scheme that can be used as standard across different countries. So two main questions that we will want to answer in a staging scheme is one is how can we assess the disease severity when a patient presents with the symptoms of COVID-19 at the baseline. Right now, the scheme that is used is based on previous experiences from diseases like the flu or the common cold or other respiratory illnesses which have staging schemes already developed, but there is no staging scheme that is tailored for COVID-19 as yet. And once we are able to decide assess the severity of the disease, then how can we recommend the most effective treatments to the patient? Even that is currently done on a trial and error basis, and we have seen that it does not work. That's why we have so many deaths and so many continuous infections with respect to COVID-19. So what we propose in this position paper is a framework that we think might be able to help develop a staging scheme on the fly, because unlike most other diseases, this is a new disease, so we have to learn these how can we assess the disease severity, as well as how we identify the most effective treatments on the fly while the pandemic is going on. So that's why we propose a framework that is online. So basically, when this framework is going to utilize existing data. For example, if we start implementing this framework right now, what we will do is we'll take the data up to now from multiple hospitals about the patients who were admitted and the biomarkers that were collected from these patients, and also the disease history, how the patients were treated and what sort of outcomes they had, whether they improved or whether their condition worsened, all of that, and the time course of the disease progression. We will use that to learn a couple of things. One is, can we estimate the severity of the disease based on the data that is collected from the patient? So that will be, that can be a probabilistic estimate whether, the disease is a mild disease or is a very critical condition. And once we are able to assess this severity, and then based on that, can we recommend what is the most appropriate course of action for this particular patient. This can be as simple as saying, okay, keep the patient in the general ward, or send the patient to the ICU, or put the patient on mechanical ventilation. So these decisions have to be, first of all, because when we have some initial data, we will be able to match whether, for certain levels of disease severity and inputs, what were the actions that were taken, and then can we learn anything from what is the best course of action. But then there is also the input of an expert in the field, because as we know, this is a new disease, and whatever we know so far from the trial and error-based approach is probably not the perfect solution. So we want expert inputs, and so the recommendations provided by our optimizer will be reinforced by an expert, and then the final decision will be made by an expert. And then for new patients, we can use these recommendations reinforced by the expert to treat their conditions as they are coming in to a hospital. So this is sort of the framework that we developed, and we believe that this can be considered as a recommender system, but I think this is not what most of the presentations have talked about so far, but I believe this still fits within the same framework. So we have some early work that we have done to see whether this sort of an approach is feasible. So we used the data of 513 COVID-19 patients from the UI Health System in Chicago, Illinois, and we used their blood biomarker data as well as their information on how their diseases progressed. So the figure here shows that, so how we assess disease progression in this case is the number of days they spend, the patients spent in the hospital before they were admitted to the ICU. For example, if a patient was never sent to the ICU, their disease is not that severe. On the other hand, if the patient had to be sent to the ICU on the first day, that means it's a severe condition. So what we find is that certain blood biomarkers that we measured from these patients have different profiles between these different groups. And more importantly, these blood biomarkers were extracted at the baseline when the patients first presented to the hospital. So that means that there is a prognostic value that can be used to assess the severity of the disease. So going forward, we would like to build on this and develop a decision scheme that can be used to recommend decisions to the patients, and we will run this optimization continuously to optimize the decision scheme as well as the disease severity estimation scheme continuously. So what are some of the challenges going forward is, in this simple example, we showed that, okay, using blood biomarkers, we can estimate severity, but there is a lot more other information from demographics to chest x-rays to the genomic profiles to various other things, which can provide different and important information that can be used to estimate the disease severity. So how do we use them and how do we combine the different information is a big question. And the other thing is, so as you know, the model predictions that are made by the decision scheme that we will have will be very sketchy at the beginning because we are starting from a small amount of data, but then with more data, it will be better. But how do we quantify the uncertainty in the model prediction so that the expert who is looking into the model's predictions can assess whether to trust these predictions or not? So there are approaches coming up to quantify uncertainty in model predictions, machine learning model predictions, including deep learning. So we hope to explore some of those directions. And the other problem we may have is what is the correct time frame for developing a model as well as reinforcing the model's predictions, because certain patients, they get better in a few days, but some patients, they stay in the hospitals for months. And so how do we measure the outcome of a recommended treatment, as well as what is the best way to reinforce the model? So that is a big question. We are still trying to figure that out. Hopefully, we will have a solution, as well as modeling the human in the loop process, because the traditional reinforcement learning based approaches are dependent on the deterministic nature of the actions that are being taken, or at least there is a probabilistic estimate of, if I take this action, this will be the outcome, right? So, but that is sort of eliminated from this process because of the human who is making the decisions. So how can we model that to correctly reinforce the model's predictions is also a big question. So we are trying to address those questions. So with that, I will conclude the talk. And so I'm new to this community, and hopefully your feedback can be useful to continuously refine our approach. Thank you.
So hello everyone. It's sort of late-ish at night where I am, but hopefully this is going to be somewhat interesting for you. It's a recommender system that a student of mine built for informal bibliotherapy. Now, I was relatively unfamiliar with bibliotherapy as well at the beginning of this project. So to the best of my understanding, I have a cartoon version of how it works and how a recommender system could potentially help with it. So basically the idea is you have a person and they have some challenges, like everybody has challenges, and there's different strategies they could use to tackle these challenges. But there's a thick fog of anxiety that surrounds this person, so they can't actually see these strategies, and that further perpetuates that anxiety. Now, the way bibliotherapy handles this all too familiar problem is that it recommends books. You go to the library, you say you're upset. The librarian recommends a book which contains a character which faces similar problems to your problems. And that character obviously has some projected anxiety within the story, but it's a transparent anxiety because there's no egocentric aspects to it. And as the reader begins to identify with the character in the book, the reader gets to see all the strategies that are potentially available to this protagonist, and then arrives at this insight at these strategies being potentially applicable for them also, which helps to dissipate their own anxiety. So this is in some ways the promise of bibliotherapy, and it seems prima facie to contain at its core a recommender system problem. In effective bibliotherapy, what is required is you have to have an understanding of the reader's condition, and you should have the ability to identify some text, some book, some reading that the reader is likely to find relatable in their condition. Now, in real life, this is obviously a very complex and sensitive task. And so for people who are clinically depressed or who have anxiety disorders, for formal bibliotherapy, this must obviously be conducted by a trained therapist. But for self-diagnosed anxiety or depression, in informal settings, could an algorithmic recommender system replace interpersonal recommendations? This is what we wanted to identify. So what we did is we built a relatively simple recommender system. And essentially, the novelty here was that every time a user interacted with our system, we asked them to write in long form how they were feeling and why they were feeling that way. So essentially a sort of a diary entry or a journal entry every time they logged in. And then based on our summarization of their responses, we gave them recommendations for texts to read. And we conducted a user study for this recommender system to see how it worked for them. And we recruited about 200 people, and we were soliciting respondents interested in improving their mental resilience. So it was not a general population sample. We got a lot of attrition, which is not unexpected for this sort of work. So 36 participants completed the study as outlined in our protocol, which was that they had to use the system at least once a week for a period of 8 weeks. And for each participant, for each session, we would make 10 recommendations, 5 of them using our system and 5 of them sampled randomly without replacement from the corpus. This was a way of trying to assess the effectiveness of our system above a random baseline. And the response variables we collected were per session mood ratings on a 1 to 5 scale and per reading relevance ratings. So every text that they read, at the end of the text when they'd read it, we asked them to say how relevant they found the text for themselves on a 1 to 5 scale. And this is also something we collected. So we have some results. I will not claim that these are final results. These are still preliminary because the data set is fairly small, 36 participants. But we found that people's mood while they were using our system improved if they found the readings relevant. That's one observation that's sort of heartening. We also found that there was no real structure in which narratives or which readings people found relevant. Different people find different readings relevant. So if somebody was to think of using collaborative filtering, you would expect some sort of clustering or block clustering structure in people's the participant versus readings rating scatter plot, or not scatter plot, but heat map plot. And we didn't find such clustering structure. And then the most interesting observation, at least to me, was that people found that personalized recommendations based on their diaries were not as relevant as texts that we were just randomly recommending. So the system actually performed worse in a statistically significant way than the random baseline. So obviously these results are very preliminary because of the small sample size. And also, given the nature of the results, we probably should be having some participants do exit interviews and self-reports, focusing on these conclusions to see if they are substantiated. But the broad takeaway that we get from this is that conventional recommender system approaches may not lend themselves very well to this setting. And this is not necessarily that counterintuitive because as I showed you at the very beginning, the core premise of bibliotherapy is that the bibliotherapy exercise, reading the book, it gives people a way of understanding their situation by adding some psychological distance from the situation in the guise of a protagonist. But if you recommend something that's too relevant or too close to somebody's situation, then that may not generate sufficient psychological distance. So that's potentially an explanation for why things worked out this way. But as I said, it is very tentative, very preliminary. So since we were meant to be in Brazil, I'll leave you with this informal bibliotherapeutic suggestion, and I'm happy to take questions or comments at this point.